Well, unfortunately, it looks like I have my microphone off for this little set of notes, so enjoy this voiceover. So last class, talked about rotational kinematics and how they related to some of the linear terms. So this problem right here is a good example of relating rotational to linear through the marching band equation. So it says in order for a compact disc player to read correctly, the surface must be spinning past a laser lens system at 1.3 meters per second. That would of course be a linear speed. Find the angular speed of the disc in revolutions per second when information is being read from these two different radii. And then it says which speed remains constant, angular or linear. So we are used to in the marching band equation, often being asked for different linear speeds of maybe the different marching band members. But in this particular problem, you have the same linear speed, that 1.3 meters per second. So that answers question C right there. The linear speed remains constant, but in order for that to happen, the angular speed and the radius would have to change. So there's our marching band equation. Linear velocity equals angular velocity times radius. Linear velocity in either case is 1.3 meters per second. And we are being asked for the angular speed. First radius is 23 millimeters. So just watch your units. If our linear speed was in meters per second, of course, the radius also needs to be in meters. Milli is a factor of 1,000, so that's 3 decimal slides. So 0.023. Then, of course, just divide, and you can get your radians per second for omega. And that's 56.5 radians per second. And you can see part A has the smaller radius, 23 millimeters, where part B has the larger radius. And if we're going to multiply radius times angular speed and get the same 1.3 meters per second, then the smaller the radius, the bigger the angular speed would have to be. So if I got 56.5 in part A, I'm expecting something smaller in part B. And also it did say convert this to revolutions per second, not radians per second. So don't forget that 1 revolution is the same thing as 2 pi radians. So divide by 2 pi. And a common mistake, make sure when you are dividing by 2 pi, you put that in parentheses. I've had lots of students over the years accidentally divide by 2, but multiply by pi when they thought they were dividing by pi as well. So it looks like we get about 9 revolutions per second for part A. Part B, same math, just plug in 0.058 for your radius. And again, this is a bigger radius than part A, so I'm expecting a smaller angular velocity in order to keep that linear speed the same, in order to keep that 1.3 meters per second the same. And when you do get your radians per second, again, divide by 2 pi. Get 3.6 revolutions per second. So obviously those were two different angular speeds you just solved for. So when it says which speed remains constant, angular or linear, it was the linear. And again, not how we are usually asked about the marching band equation. Often it's like, of course the marching band is sweeping out the same angle, they're going around a turn, maybe making a 90-degree turn, but different band members have different radii, so they all have different linear speeds. Okay, and that was a little recap of relating linear motion to rotational motion. Okay, the next topic in chapter 11 here is rotational kinetic energy, which leads into something called rotational inertia, or moment of inertia. But we know from linear motion that kinetic energy is 1/2 mv squared. So we can sort of relate this for the moment, keeping the m, although that's going to change, but 1/2 mv squared, what did we just learn as the new rotational variable for velocity? Well, we learned it is omega. And we'll see in a little bit how the m changes as well, so that we have 1/2 times something really times omega squared. But at any rate, talking about rotational kinetic energy, we've got 1/2 m omega r squared, plugging in our marching band equation. But this is not the most helpful equation right now because there's just the one m. Are we talking about one mass? What if it was that CD player from the slide before? Well, there's a different radii that corresponds to every little piece of plastic of that CD. So if I have anything other than just a point mass, I have to multiply the mass of that thing times its radius, and then sum them all up. Now, for symmetrical objects, there's going to be an easier sort of formula for all of that. But right now, we'll just kind of talk about point masses for a moment. And this idea is called moment of inertia. Not just mass, but where that mass is. Mass times radius squared. And think about inertia back in our forces unit. The word inertia means resistance to change in motion. Resistance to linear change in motion. And that only depended on mass. So, for example, like an elephant has more inertia than a mouse. It's harder to change what an elephant's doing than to change what a mouse is doing, just based on mass. But in the rotational world, if I'm talking about trying to get like a tire to rotate, an 18-wheeler's tire or a sports car tire, even if they had the same mass, they're going to have different rotational inertias. It's going to be harder to get that 18-wheeler tire going or stopping or really just changing whatever it's doing than a tire of the same mass but a smaller radius. So in the rotational world, it doesn't just matter what the mass of the object is, but what that radius is, what the distance away from the point of rotation is. The farther that distance away is, the more rotational inertia it would have. Okay, but the point mass idea, you will need to memorize that formula. Moment of inertia for point mass was mr squared. Anyway, so this is what we're talking about. Inertia is resistance to change in motion. In the linear world, just related to mass. In the rotational world, it relates to mass, but also where that mass is. Later on, when we do conservation of angular momentum, we'll talk about like the figure skater. And the figure skater, she's got the same mass regardless of whether her arms are apart or tucked in. And, if her arms are spread out, she's got a much greater resistance to change, much greater inertia when her arms are out, and she would spin slower. Of course, this relates to momentum. But when she tucks her arms in, still the same mass, but she has less resistance to change and much smaller rotational inertia there. So just reading that second bullet point, resistance gets greater with mass, but for rotational motion it also increases as the mass gets farther from the axis of rotation. Okay, so here's a little demo I like to do. I wish this would show a little slow motion, but I have these two sort of cylinders. One's sort of like a hoop because it's hollow, and one is solid, but they have essentially the same mass, but yet they won't roll the same way. Predict which one will roll faster, the hollow or the solid. Alright, now I wish I had a little slow motion or zoomed in a little bit, but the black cylinder there was the solid cylinder, and it rolled sort of faster, kind of beat the hoop, or that little cylinder with a hole in it. And even though they had the same mass, that's the perfect example of rotational inertia. The solid the solid black cylinder has its mass, more evenly distributed, whereas sort of the hoop, the hollow cylinder there, has its mass spread out and farther away. So where the mass is farther away, that is more rotational inertia. It is harder to change what that object is doing. So therefore, it took a little longer to get going, basically. So there's more rotational inertia for the hollow cylinder than this solid cylinder. So that leaves us with our first rotational inertia formula, which is just mr squared. This would be summing up a bunch of different point masses. Again, we'll relate to different shapes in a moment there. But now that we have that formula, we can go back to this kinetic energy problem. So we have 2 point masses here, on the left and right of this lightweight rod. It says 2 masses are attached to a lightweight rod, and where it says lightweight rod, that means we're going to ignore the moment of inertia of the rod itself. Just pretend the rod isn't there, they're just magically connected somehow. So the 2 masses are attached to a lightweight rod rotating about an axis perpendicular to the rod at the center of mass. One's got a mass of 2 kilograms, the other 1 kilogram, and the rod itself is 3 meters long. If the masses are rotating at 4 revolutions per second, what is the total kinetic energy of the masses? So here's where we've plugged in the I in our kinetic energy formula. Think of the linear kinetic energy formula, 1/2 mv squared. Well, it's sort of the same thing. I stands for rotational inertia, so that substituted for mass. Mass is just sort of regular linear inertia. And then instead of v for linear speed squared, we have omega for angular speed squared. So it really is the 1/2 mv squared formula. I just need to realize that my I is a combination of 2 point masses, where the point mass formula was mr squared. And I do need to be in radians per second, so we're just converting that 4 revolutions per second to radians per second. Again, remembering 1 revolution is 2 pi radians. So, a little extra work to convert your angular speed. And now we need to plug in for I. And again, there's 2 point masses, so we're just doing mr squared twice. I'm just going to sum that up. There's only 2 of them. what would the radius be if this rod is 3 meters long and it's rotating about the middle? Okay, good. So 1.5 meters would be the radius. So just multiply the first mass times radius squared. And then the second mass times radius squared. 1 times 1.5 squared. And then just sum that all up. And that is the total moment of inertia of the whole system. And moment of inertia, think of the formula: mass times radius squared. Those are the units. Mass is in kilograms, radius is in meters, so kilogram meters squared doesn't really have a special unit other than that. So now that I've found the rotational inertia, I've found my angular speed, just plug that all into the kinetic energy formula: 1/2 I omega squared. Final answer, apparently 2131.4, and this is energy, so same energy units we've always dealt with. Throw a J for joules on the end of that. Okay, so that's a rotational kinetic energy formula. Alright, so moving on to the next slide. Says Clint is standing on a platform that can rotate. Which moment of inertia is greater? When he rotates with his arms at his side, when he rotates with his arms out? And think about which would have the most resistance. Well, similar to that figure skater, Clint has the same mass in either situation, but if his arms are out, then some of his mass has a greater radius than it would otherwise. If his arms are tucked in, then his arms have a smaller radius. So, moment of inertia is based on mass times radius squared. There would definitely be a greater resistance to change with his arms out. Okay, sorry to skip those last two checkpoints. But anyway, so now talking about those different shapes. I had to sort of mention a hoop and a solid disc. They all essentially use that mr squared value, but you're summing every little mass, like every little molecule and its radius. So there are formulas that we can come up with sort of by integrating the radius squared with respect to a little mass division. But we're going to skip some of those integrations. At the very end of the year, we'll come back and maybe do one and prove where all these formulas came from that are in your notes here. But I do ask you to memorize, I think, 4 of them. The point mass, of course, then a solid cylinder, a hoop at the top left, and a slab at the top right. So just a real basic moment of inertia problem, just finding that I value. Calculate the moment of inertia for a car tire. Assume the mass is 25 kilograms. The inner radius is 30 centimeters and the outer radius is 50 centimeters. So we sort of call this a hoop. It's just not like a thin hoop. A thin hoop we would pretend has just one radius. But you can look this one up. But when you have the 2 radii, that's the formula you're going to use: 1/2 m r1 squared plus r2 squared. And then just watch your units. Centimeters, of course, factor of 100, so move that decimal twice. So the inner radius is 0.3 and the outer radius is 0.5. Don't forget to square your radii values. Mass was fine in kilograms. And looks like we get 4.25 kilogram meter squared. Okay, and our last topic today is called the parallel axis theorem. Still relates, of course, to moment of inertia, but all of those formulas in the notes, and that are also in your textbook, assume, well, except for one, assume that the object is rotating about its center of mass, which it certainly doesn't have to be. This slab, for example, could be rotating about the center of mass with that axis drawn right in the middle, or it could be rotating about that axis sort of off to the left, in which case you can easily come up with the moment of inertia there, and should make sense that it's higher. It would have the same mass, same slab, but now all that mass is farther away from the rotational point. So since moment of inertia relates to radius, it's going to have a greater moment of inertia. Anyway, that formula there, moment of inertia I for some random axis is the original moment of inertia formula, so I like little cm, here you go, plus mh squared, total mass. Now h is the perpendicular distance from the center of mass's axis to your new axis. So this says, look at the page in the book or the slide of notes there. What's the only shape that's not rotating about the center of mass? Well, there's a rod rotating about the end. So the rod rotating about the end is not obviously rotating about the center of mass. So we're going to see if we can come up with the same formula that's in the notes. So we can look up a rod rotating about its center, and that's the 1/12 ml squared. Throwing in the mh squared part for the parallel axis theorem, of course m is m, but h is the distance from the center of mass's axis to the new axis, so that's why we said half L. That is a straight line perpendicular distance between those two axes. Now, of course, you're squaring a fraction, so be a little careful there. Half squared is a fourth. Make yourself a little common denominator. You got a 1/12 ml squared and then a 1/4 ml squared. So turn that fourth also into a 1/12, and 1/4 would be 3/12. So 1/12 plus 3/12 gives you 4/12, which is the same thing as 1/3 ml squared. And that is exactly what the I value given in the book is, or the slide of notes there. Moment of inertia for a rod rotating about its end and not the middle is 1/3 ml squared. That's called the parallel axis theorem. Just be careful about that h value in the formula. That has to be the perpendicular distance from the center of mass's axis to wherever your new axis is. Okay, sorry about the audio on this one.